We're going to be talking about the van der Waals equation and how we can derive the excluded volume and attractive interaction factors in the van der Waals equation, all because of a pressure versus specific volume diagram. So let's get started by drawing a pressure versus specific volume, which is the volume divided by the moles or the mass of the substance, and a graph of that, what that usually looks like. So right here we'll have a curve, and this will be at 3 different temperatures because the curve will change dependent on the temperature. So right here we say we have one that is at a temperature that is greater than the critical point which we discussed in our previous video. Right here we'll have a pressure curve at the critical point. T is equal to Tc. And here is a final isotherm that is below the critical point temperature. T is less than the critical temperature. As you can see, they behave slightly differently depending on their temperature. And that difference, if you note right here and right here, this one goes completely flat. And that is because there is an actual curve on here, a parabola, that marks the boundary between the liquid and the gaseous phases. So right here, this is entirely liquid, put a big L there. And this here is entirely vapor, so I'll put a big V here. This right here is both liquid and vapor. And because both the liquid and vapor phases are present, the pressure cannot change. Remember, that's determined by the temperature, as by the Antoine's equation. So we know that when we're in the both liquid and vapor state, in between liquid and vapor, the pressure in the system is going to be constant because at this specific temperature, the Antoine equation will tell us the vapor pressure no matter what the specific volume is. So, if you notice right here, since this is below the critical temperature, it cuts through this parabola and becomes completely straight. However, this one at the critical temperature only barely touches at one single point. And you can also tell, when we're looking at it, and the way the curve looks at the critical temperature before and after, that not only does the derivative become flat here, but also the curve goes from upwards to downwards, which means this point is also an inflection point. Now, this is important when we come to the van der Waals equation. Now, we know PV equals nRT, pressure times volume equals the moles of a substance times the gas constant times the temperature. However, we also have to remember that when we're talking about specific volume, which is, again, volume over the amount of substance, meters cubed per mole, there is no n in PV nRT. So what we actually have is PV, now this is specific volume, so I'll just notate that with a VM, is equal to RT. Now from here on out, I'll be using a smaller lowercase v to indicate it's VM, which is the specific volume. But what van der Waals does is, first he moves that v over, so we have P is equal to RT over V. But what van der Waals says is, well, this applies for ideal gases. What happens when a gas is non-ideal? So what he does is he adds terms to this equation to make it apply for non-ideal gases. So the first thing he does is says, well, the volume available to the gas to make pressure, to bounce along the edge of the container and cause pressure, is not just the volume of the container, it's the volume of the container minus the volume that the gas particles take up. And he notated that with a minus b right here on the bottom of the fraction. And then what he also said is, because these gases are not ideal, they're going to interact with each other. So what he did was he added a subtractive factor right here, which indicates the attractiveness between particles interacting in a container. So he notated that as A over V squared. Now the question, A is some constant which depends on the substance, and V squared, this is actually interesting, derives, why is it V squared and not just V or V cubed? Well, it's because the only molecules that will be experiencing an attractive factor, a net attractive factor, are molecules near the outside of the container. molecules near the inside will be attracted to all the particles surrounding them in all directions, and so it will roughly cancel out. So it would be the attraction of those particles is 1 over v. However, the only particles that feel that attraction are the ones near the outside of the container, which is roughly proportional to 1 over v. So only the particles with the 1 over v amount of particles that are near the edge of the container are feeling an attractive force of 1 over v. So when we combine that, we get 1 over v squared, and then of course A is that constant factor that applies for each individual substance. So, how exactly do we figure out what B and A are? Well, we can use the critical temperature to derive these two thanks to our behavior on this graph. As I said earlier, at the critical temperature, the critical volume, which is this volume right here, V of C, we are going to end up at the critical pressure, PC. And what we see at the point VC and PC, which is at the critical temperature, we see that, as I discussed earlier, this is an inflection point because the curve goes from upwards to downwards. And also, the slope of that line, the slope of the isotherm there, is 0. So we know that the derivative of this equation, so E prime at T is equal to TC and V is equal to VC. We know the derivative of this is, it's going to take me a second to calculate this out right now. So it'd be RT are both constants, so it'd be RT, and V is plus A plus 2A over V cubed over here. And this is a derivative of V. It's going to be V minus B. So it's just going to be two would be negative. So this is our derivative, and we can see right here at TC and V of C, it is equal to 0, because again, the slope of that line is 0. Even if my graph doesn't illustrate that, that is true. And also, we see that the second derivative must be equal to 0 because it's an inflection point. So we'll calculate P prime at T is equal to TC and V is equal to VC. Of course, we're taking this derivative also with respect to V. So the derivative of this is going to be negative RT at the top. This is going to become positive 2. It's going to be V minus B cubed. This is V to the third, so that's going to become minus 6A over V to the fourth, I think. Because yeah, it's 2 to the 6. You know, this is also equal to 0. This being our second derivative. And it being also equal to 0 because on that graph at T of C, we have an inflection point. So what we see here is that we have two equations and two unknowns, A and B. We're going to begin manipulating them algebraically in a way that it can be solved. So first, we're going to move this over to this side and move this over to this side, so both halves of the equation become positive. So we have RT over V minus B squared is equal to 2A over V cubed. When we move this 6A over, we'll have 2RP over V minus B cubed is equal to 6A over V to the fourth. And what we notice now is that these powers are offset by 1 from these powers on the bottom half. So if we take the inverse of this whole equation, -1, and then we multiply them together, by this equation right here, it should, in theory, cancel out the majority of the powers of these v's and also clean up some of the constants kind of nicely. So we'll start doing that now. So we flip this over and multiply them. We'd have minus vb over 3 over vb over 2, so we just have v minus b up top. And 2rt on the bottom and rt on the top would leave a 2rt on the bottom, or just a 2 on the bottom, like that, and those rt's would cancel out. And that would be equal to, well, we have v to the 4th over v over 3, so that would just be v on top. And then we'd have 2a over 6a, so that would just leave us on the bottom having 3. And this equation is significantly simpler than what we had up here. So, only b is remaining, so we simply begin solving for b. We multiply by 2 and by 3. We have 3 v minus b is equal to 2v. We're going to distribute this in our head and then move everything over. So subtract 2v from both sides, add 3b to both sides, and we end up with v is equal to move that over, is equal to 3b. When we solve that again, move that, divide by 3, we get v. b is equal to critical volume over 3. So, the critical specific volume divided by 3 is b. That's a pretty significant discovery. So all we have to do now is plug this into either one of these equations right here and get a. So, having had to move over for space, we're going to continue by deriving a using the value of b we have just calculated. B being the specific volume at the critical point divided by 3. And we're going to take that b value and plug it into one of the two equations that we've just solved previously, or at least derived in our pursuit of b. So we're going to use the first one because it's a little bit simpler. That says RT over V minus, now this is B, so remember that's VC over 3 squared is equal to 2A over VC cubed. And again, since we're doing this in terms of the critical point, we need to have the critical temperature and critical specific volume notated here. And as we continue to do our algebra, we can see that this just becomes VC times 2/3, that being squared, becomes 2/3, that's 4/9. So 9RT over 4 VC squared is equal to 2A over VC cubed. And now all we have to do is multiply both sides by VC cubed and divide both sides by 2, and we'll have A left by itself. So A is going to be equal to 9, let's see here, that's going to be 9/8 RT VC, seems to be a C, VC. Right there, because the VC over 3 cancels out the VC over 2 and leaves one VC behind. We see that this is our value for A. Now we're going to continue our derivations by going after a new variable, which we're going to call Z, which is known as the compressibility factor. Now the compressibility factor is equal to the ideal gas law, PV equals RT, where the R and T are moved over to the same side. So Z is equal to P specific volume over RT, which in the case of an ideal gas is equal to 1. However, when we're talking about a non-ideal gas, that's van der Waals equation, which has the extra negative B term and the negative A over V squared term added in, the compressibility factor is not 1 any longer, because those A and B variables, which vary depending on the substance we're talking about, change and affect that compressibility constant because they're no longer an ideal gas. So, how can we figure out what Z is specifically at the critical temperature, critical pressure, and critical specific volume of substances? Well, we can use A and B, and by plugging them into van der Waals equation, we can solve for Z in terms of those these variables specifically at the critical temperature. So if we draw out van der Waals equation again, P, this time of critical, because we're talking about specifically at the critical point, is equal to, let's see, R T critical over V critical minus B, which is V critical over 3. That's minus A, which is 9, 8, R PC VC over VC squared. And when we look at these equations, we say quite easily this can be simplified, and these two VCs, both on top and bottom of the fraction, can be simplified. And we can rewrite that as R PC over VC, and now 1 minus 1/3 is 2/3, but since that 2/3 on the bottom of the fraction, we're going to flip that around to be 3/2 minus, even 9/8 there, R and TC, and then VC on top, VC squared on the bottom, they cancel to leave one VC exclusively on the bottom. So we have R TC over VC, that's all still equal to the critical pressure. And we see right here that this fraction that contains all of the variables and this fraction that contains all the variables are exactly the same, and they only differ by the constants. So we can do this subtraction. I'll do the fractions right over here. You have 3/2 minus 9 over 8, and we can get this into a common denominator by multiplying this by, well, this just by 4, and then they'll work out. So right here, 4 times 4, we have 12 over 8 minus 9 over 8, and that gives us 12 minus 9 is 3 over 8. This is going to be our new coefficient once we complete this fraction subtraction. So we have P of C is equal to 3 over 8 times R TC over VC. And we notice that if we multiply this by VC, both sides, and divide both sides by RTC, and the TC is kind of hard to read there, but it is a TC, we notice that we would have PV over RT, although in the critical versions of those variables, which is exactly what our Z is equal to. So when we do that division and multiplication, we get PC VC over R TC is equal to 3/8. This tells us, by the definition of the compressibility factor Z, that the critical compressibility factor of all substances is equal to 3/8. Because notice, our original compressibility factor for all ideal gases was always 1, no matter what. However, by integrating the A and B into the van der Waals version of the equation, we were meant to simulate non-ideal gases, gases that interact with each other's particles and also have attractive forces caused by intermolecular variations in the electron cloud. So what we see is when we plug the derivations of A and B we've arrived at using our critical temperature, critical specific volume, and critical pressure, and break that definition down into its simplest form, we find that the critical compressibility of all substances, no matter what their A and B constants actually are, outside of the critical point, because these hold true only at the critical point, because that's why it's TC and VC, and also VC down by B. 9/8 RT times V does not hold true for anywhere except the critical point. And what we find, after, again, doing all of this algebra, is that no matter what A and B are, no matter what substance we're talking about, the critical compressibility, the compressibility of a fluid or gas at the critical point, or because it's a fluid, it's no longer a liquid or a gas, it's a fluid at the critical point, is always 3/8. No matter the substance, no matter what the actual critical point is, at that critical point, the critical compressibility, the compressibility factor Z, is always 3/8.